Thank you for your patience. Welcome back to ECE 501B. Homework 5 is due in a week. Today what I want to do is get through the rest of Chapter 5. That's the plan. And what I've tried to do is indicate what that represents in terms of the propositions and theorems that we will work through or simply talk about. We'll spend a little bit of time with proposition 512, proving that. It's basically three statements that are equivalent for an upper triangular matrix. What I want to do today is first give you an example of an upper triangular matrix that we will look at, or that you can kind of keep in your hip pocket and work through all of these relationships if they're not making sense in the abstract or in the general setting. We will talk about proposition 512, which is an upper triangular matrix. What does that mean relative to invariant subspaces with respect to the matrix representation of an upper triangular matrix? And there's relationships that we can think about or keep track of. We'll go through the proof of that, but then we'll simply present a lot of these others as just results or facts. Proposition 516 says if you have an upper triangular matrix representation of a linear map T, and then that matrix is invertible if and only if all of the diagonal entries on that upper triangular matrix are non-zero. That's a fact. Another fact is our eigenvalues are those diagonal entries on that upper triangular matrix. Another fact, if the underlying dimension of our vector space is little n, Nevada, and we have actually n distinct eigenvalues, then that matrix representation in that vector space can actually be diagonalized. We can actually improve upon the upper triangular, and we can make everything just appear on the diagonal with respect to a particular basis. And that basis set is actually the set of eigenvectors. And that provides us then with a direct sum decomposition of our original underlying vector space. A lot of this goes away. These nice results are no longer true when we restrict our attention to having real numbers or a real vector space. Our field of numbers becomes real. When that happens, then we don't have all of these nice general or generic properties. And that's the distinction that I hope to get to, and that's where Chapter 5 finishes relative to linear operators. We're working with linear operators. We're mapping from a vector space back into itself. When we do that, then we can have these concepts of eigenvalues and eigenvectors. And eigenvalues really just say that that's the amplification or the scaling in a particular direction relative to how that maps on or responds to a direction that is an eigenvector. Let's now look at a specific example. Here's an upper triangular matrix. It's a linear map, and I'm actually going to restrict it to the real numbers so that we can sort of keep this all in our head. But the linear map is in this three-dimensional space. And I'm going to call this matrix A, since that's typically what I like to call my matrices, is A. But A is going to be the matrix representation of this linear map, and I'm going to use for my basis vectors the standard basis so that we can think in terms of X, Y, and Z when we're viewing this linear map. Let's then assume that this upper triangular matrix has a matrix representation with the following structure. Triangular means that everything below the diagonal is set to 0 or will be 0, and what's above the diagonal is it's anything. It could be some zeros, but in general, it's non-zero values. Let's just assume that this is our prototypical example of an upper triangular matrix. It's an operator, so it's mapping from a 3 space to a 3 space, or from R3 to R3. That's what an operator does. It maps from the domain back into the codomain, which is also the domain. If we now look at trying to find the eigenvalues and eigenvectors for this upper triangular matrix, we can do that from the basic equation, the eigenvalue eigenvector equation, which is ax equal lambda x. If an x exists and a lambda exists that satisfies this equation, then we know that we have this relationship, a minus lambda I times this vector x is equal to 0. Or another way of saying that is for a given eigenvalue lambda, this vector x, if it's operated on by this matrix operator a minus lambda I, it must live in the null space of a minus lambda I. Lambda we would have to find or use as an eigenvalue of that original matrix A. Here is, we're sort of foreshadowing what we're going to state in the future, but for an upper triangular matrix, the eigenvalues are on the diagonal. And we'll show that, or we'll just state that as one of the results in Chapter 5. But if we buy that now, or if you accept that, if you looked back at that matrix, on the diagonal we had a 2, a 4, and a 5. And I'm just going to call those eigenvalue 1, eigenvalue 2, and eigenvalue 3 for this generic example. Eigenvalues are then 2, 4, and 5 for this matrix A. Now, we can find the eigenvectors by examining the values or the vectors that will live in the null space of this matrix for these 3 different choices of eigenvalues, 2, 4, and 5. We're going to then play with this matrix when we have lambda equal to 2, lambda equal to 4, and lambda equal 5. And hopefully in all 3 of those cases, we will find a non-trivial vector that when operated on by this resulting matrix, a minus lambda I, will produce the 0 vector. It'll map us into the 0 vector. The definition, really, of an eigenvector. If we do that, then let's say we do it for the eigenvalue lambda equal to 2. Then if we plug in 2 here, we see on the diagonal that we will end up with 0, 2, and 3. And that's what we have on our diagonal. And we're not changing anything else in the matrix. We're just subtracting lambda I from our original A matrix. What we now end up with is a matrix that hopefully has a non-trivial null space. And it better be somewhat clear that since the first column is all zeros, we have some linear dependency among the columns in this resulting matrix, or we have some linear dependence among the rows in this matrix, and that means we do have a non-trivial null space. Meaning if you looked at these rows, I hope it's clear that the first and the second should be, how do I want to say this? Dependent on each other. Meaning there's no term in the first column, and so there's only 2 non-zero entries in the 2 rows, and so we can actually show that one is related to the other. if we now try to solve, so this set of equations, this matrix A minus lambda I with lambda equal to 2 times a column vector x equals 0 really gives us 3 separate equations. And if we sort of work from the bottom up, we'll maybe see some relationships on these components, x1, x2, and x3, of our eigenvector that has to be true. If we look at the third row, see that we have 3x sub 3, and that's supposed to equal 0. Well, that immediately forces x sub 3 to be a hard 0. Does everybody see that? If we need that third row to be true, that says 3 times x3 is equal to 0. Well, x3 has to be 0 for that to be true. All right, let's go to the next equation, the second row. That says we have 2x sub 2 plus x sub 3 equal to 0. But we've already found that x3 is 0. If we plug 3 or 0 in for x sub 3, we see that 2x sub 2 is 0. Well, the only way that can be true is for x sub 2 to be 0. Now we've fixed x2 and x3 in this eigenvector to be hard zeros. Let's look at the first row. That says we have 0x1 plus 3x2 minus x sub 3 equaling 0. But we've already fixed x2 and x3 to be hard zeros. x1 times 0 needs to equal 0. That's pretty easy to find an x1. x1 can be anything, can't it? Well, let's make it something fairly benign. Let's just pick it to be 1. So now we've determined for an eigenvalue of 2 in that original upper triangular matrix, which was in the 1, 1 entry, that was our eigenvalue, we have an eigenvector of 1, 0, 0. That's the direction. So now anything on the x-axis for this matrix will get mapped immediately back onto that x-axis when we hit it with that A matrix. We can do the same thing for the other 2 eigenvalues. If we plugged in lambda equal to 4 to A minus lambda I, our top 1, 1 entry was 2 minus lambda. 2 minus 4 is going to be minus 2. The 2, 2 entry was 4 minus lambda. That's going to be a 0. And the last entry in the 3, 3 entry on the diagonal was 5 minus lambda. 5 minus 4 gives us 1, and we're not changing any of the other elements in that matrix, A minus lambda I. Well, if we look at this, this now gives us 3 equations that need to be true. And I hope that you can see that from the last 2 rows, that's forcing x sub 3 to be 0. The bottom row says x3 is equal to 0. The second row says x3 is equal to 0. So let's just take it. x3 is equal to 0. If we now look at what the top row produces, we see that minus 2x1 plus 3x2 minus x3 must equal 0. But we've already concluded that x3 is a hard 0. Now we see that we have this freedom in our selection of x2 and x3 if we choose something that's kind of clean, meaning let's choose x sub 2 equal to 2, then we see that 2x1 needs to be 6, or x1 is 3. And now we have our second direction, our second eigenvector with respect to the second eigenvalue 4. And this one, if you're thinking in terms of 2-dimensional space or 3-dimensional space, the z direction is nothing, and the xy plane, we go over in the x direction 3 and up 2 in the y direction. And that's not aligned with the x-axis, is it? So these 2 vectors, eigenvectors, the first 2 that we found, aren't orthogonal, but they're not on top of each other either. They span all of the xy plane. Okay. If we carry this on a little further, we only have one more eigenvalue to do, lambda equal 5. We plug that in to our diagonal, and we end up with -3, -1, and 0. That forces some conditions on these components for x1, x2, and x3. The bottom row is pretty easy to solve, isn't it? That says 0 equals 0. Okay, that doesn't give us any good information. But if we look at the second row, we see that -x2 plus x3 equals 0, or x2 is equal to x3. Top row says we have -3x1 plus 3x2 minus x sub 3 is equal to 0. If we replace x3 with x2, we see that -3x1 plus 2x2 must equal 0. And again, we can pick some nice values for x2 and x3. If we pick x2 to be 3, then x1 is going to be 2. But we already knew that whatever we picked for x2, that's what had to be x3 also. And now we have our third eigenvector, 3, 3, 2. That one says we go over 2 in the x direction, up 3 in the y, and up 3 in the z. And that's not aligned with the first two. And those three vectors span all of R3. That's now our eigenvalues and eigenvectors for this upper triangular matrix, and I hope you can start to see some structure in those eigenvectors. This one only has a component in x. The second one doesn't have a component in z. It's still in the xy plane. The third one, it has a component in x, y, and z. Something else to keep in mind. Our standard basis vectors we picked as v sub 1, v sub 2, and v sub 3. By context, I hope it's clear that v1 is not an element of a vector. It is a vector. v2 is a vector, and v3 is a vector. v1 is x-axis, v2 is the y-axis, v3 is the z-axis. What if we hit the first standard basis vector v1 with a? 1, 0, 0. That just says pull off the first column of those three columns in A. And that first column is 2, 0, 0. That's still on the x-axis, isn't it? AV1 then is in the span of our first eigenvector. So AV1 is contained in the span of V1. Let's see what happens with V sub 2. AV sub 2. Well, we just pull off the second column of those three columns in A, and that gives us 3, 4. Well, 3, 4 is just somewhere in the xy plane, and that's spanned by the first and the second of our basis vectors, V sub 1 and V sub 2. AV sub 2 then is in the span of V1 and V2. Likewise, or similarly, AV sub 3. We pull off the third column of that A matrix, and now we're at -1, 1, 5. Well, that can be represented as a linear combination of V1, V2, and V3. AV3 is contained in the span not of V1, not of V2, but of V1, V2, V3. Now what we want to do is, that is sort of our prototypical example. Keep that in the back of your mind as we talk about these more general or generic concepts in Chapter 5. When we start talking about eigenvalues, eigenvectors, invariant subspaces, this should show you that V1, V2 is an invariant subspace for A when we start within V1 and V2. If we picked a vector in V1 and V2, and if we operated on any vector that's a linear combination of V1 and V2, we're going to end up in that same subspace. V1, V2 forms an invariant subspace of A. V1 forms an invariant subspace of A. If we start on the x-axis and we operate on that point or that vector with A, we jump right back on that x-axis. So that x-axis is invariant with respect to this matrix representation. Let's now introduce some of these results in Chapter 5. And now maybe these Chapter 5 concepts will make more sense after we've seen a concrete illustration of an upper triangular matrix. Let's start with Proposition 512. Proposition 512 says that if we have a linear operator T, and V it's probably stated in the book that that's a complex, finite dimensional complex vector space. So T is a linear operator on that space, and let's say that V1 up to V sub n is a basis on V. The following statements are equivalent. The first statement is the matrix representation of that linear operator T on this set of vectors, basis vectors. That's the notation of script m of T in the square bracketed of T, with V1 being our basis set. And an operator says we're mapping from one vector space back into itself, so we really only need one basis set or set of basis vectors. Here's the first statement. Let's just say that the matrix representation of that linear operator is upper triangular. And I might abbreviate that as UT. Not the University of Texas, but just U period T period, okay? So there's no hyphen with a city after UT. It's upper triangular. All right. B. So A is equivalent to B, B is equivalent to C, so A is equivalent to C also. But B says that T, operating on a vector V sub L, where V sub L is one of these basis vectors, is contained in the span V1, V2, up to V sub L. For each L equal 1, 2, up to N. So that says that T V sub 1 is in the span of V1. T V sub 2 is in the span of V1, V2. V sub 3 is in the span of V1, V2, V3. Does that sound familiar? That's what we were doing with our upper triangular matrix a minute ago. So now we're saying so the question was, how do you arrange your V1, V2, V3? I hope that you can see that our earlier example illustrated how we could do that. That upper triangular matrix, if we have our eigenvalues ordered along the diagonal, then our V1 would be associated with lambda 1, V2, lambda 2, etc. And that would be our ordering for these V's. So we're going to assume that we have this set of eigenvectors, or this set of basis vectors, v1 through v sub n, that satisfy this set of conditions. So in this basis, the matrix representation is upper triangular, and T v sub L is in this span. And we'll show maybe that will help when we start proving this, how that might happen. The third statement is that the span of V1, V2, up to V sub L is invariant under T for each L equal to 1, 2, on up to N. The proposition said A, B, and C are equivalent statements. So we can prove this many, many different ways, but the way that I'm going to do it is I'm going to show that A is equivalent to B and B is equivalent to C. That means that A and C are equivalent because I know that A can go to B and B is equivalent to C. Okay? So here's what I'm going to do. The first thing I'm going to do is A is equivalent to B. I'm going to try to show the equivalence of A and B. And to do that, I need to show it goes in both ways. A implies B, and B implies A. So let's look at A implying B. What does it mean to have a matrix representation of T that's upper triangular? So let's consider this matrix representation of a linear operator T that's upper triangular. That's condition A, or statement A. If we looked at the nth column in that matrix representation, hopefully you can remember that the matrix representation just pulls off coefficients that we need to create the linear combination of that column or that operator. So the nth column of this matrix representation of T is the expansion of, let's say, T v sub L in the basis vectors that we've picked. And we've picked V1, V2, V sub N. Hopefully, though, you can tell me what the nth column of an upper triangular matrix looks like. What's the structure in the nth column of an upper triangular matrix? If I said, okay, here's a column, and it's the nth column. Then if I say that's the nth row, what do you know about that? There's all zeros down here, isn't there? And up here, it's non-zero. So here we have L elements, and here n minus L. Or if we wanted to put some specific coefficients in there, we would say, oh, the first one, let's say, is non-zero. The second one is non-zero. And those first coefficients are associated with the first or the second or the third basis vector. That's how we scale it. And we just keep going down until we reach the LL, and then everything else is 0. That's now what the nth column of A looks like. Or if you wanted to think about it in terms of that matrix representation, or that vector column representation, A1L scales V1. And that's added to the second basis vector, A sub 2L. And that goes all the way to A sub LL with the nth vector. But then after that, we have 0 times V sub L plus 1 and 0 V sub N. That's another way of thinking about what we're saying about the nth column of the basis, of the matrix representation of this linear operator T. Well, hopefully that is clear then what this means. That means that this linear operator operating on V sub L is expressible in terms of only the first L basis vectors. I hope that's clear from that expansion. We only used non-zero coefficients for V1, V2 up to V sub L for the nth column. That means then that TV sub L is an element of what spanning set of vectors? It was some linear combination of V1, V2, V sub L, so it must be in the span of those same columns. And this was true for any L. And I hope that's statement B. Wasn't statement B that T V sub L was contained in the span of V1 through V sub L? We started with statement A that the matrix representation was upper triangular. We showed what that looked like physically, and that led us to conclude that T V sub L is contained in the span of V1 through V sub L. So we've shown A implies B. Right? Now what? We wanted the equivalence of A and B. So now we need to show that B implies A, right? I hope. So now B implies A. B implies A said, well, what did B say? B said that we had TV1 was in the span of V1. TV2 was in the span of V1, V2. And we just keep going, where TV sub L is in the span of V1, V2 up to V sub L. Well, if that's the case, we can actually make this a little bit more concrete. We can actually assign some linear combination of V1 in the top row, V1 and V2 in the second row, and in the nth row, some linear combination of the V's 1 through V sub L. And if we're really clever with the linear combination, the result will just jump right out at us. Meaning, we can now say that T V1 is equal to alpha 1, well, let me just say alpha 1, 1 of V1. Why am I making my V's different? What's T V sub 2? Well, that's a linear combination of V1 and V2. So let me call that alpha sub 1, 2 V1 plus alpha sub 2, 2 V sub 2. Well, let's keep seeing if we can see a pattern. TV sub 3, alpha 1, 3 V1 plus alpha 2, 3 V2 plus alpha sub 3, 3 V sub 3. And we could just keep going. TV sub L satisfies that same pattern. We have alpha 1, that's going to scale the V1 basis vector, but this is for the Lth column, TV sub L. Alpha 2L V sub 2 all the way to alpha sub LL V sub L. And if we put all of those alphas together in a matrix, we have alpha 1, 1 and 0. If we look at the top row, which is still on the screen, we can just copy that down. The alpha 1, 2 is in the first row, second column, and it's going to pull off V1. Alpha sub 2, 2 is going to be scaling the second vector. And we just keep going, and we'll have alpha sub 1L, alpha sub 2L, all the way down to alpha sub LL, and eventually we would get to alpha sub NN. But what's that say about T? If that's our matrix representation, I hope it's clear that T is upper triangular. And what did we start with? To derive that, we started with B. All of this relationship, TV sub 1 is in the span of V1. TV sub 2 is in the span of V1, V2. All of that allowed us to conclude that T is upper triangular. This now allows us to say that B implies A, and with those two, we now know that A and B are equivalent. Is that okay? We're halfway there. We've shown A and B are equivalent. We want to show that 3 statements are equivalent. Let's now look at B being equivalent to C. And maybe in a lot of textbooks you might be just told by definition of the invariance of T. By definition of invariant. Remember, you're trying to learn how people maybe write proofs, and maybe they leave out quite a few steps. And what you're learning is the magic between step A and step Z. You're going, oh, I can fill in that magic. I now know what's happening. But somebody might say, by definition of invariant, B is equivalent to C. But let's now see if we can sort of understand that statement. What if we want to show that C implies B by a contrapositive argument? Do you remember what that means? That means we need to start with not the ending statement, which in this case is B. So we now want to say assume not B and from that assumption of not B, show that not B implies what? The original statement, which is, whoops, I have too many nots, not C. If we can show that not B implies not C, then we've demonstrated that C implies B by the contrapositive argument. Good thing we don't have any tails, or we'd be chasing our tail all the time, huh? But that's what we're doing. We're trying to show that all of these are connected in some way. All right, so what does not B say? B was about this T V sub L being in the span of V1 V sub L, but we want to say not that. So let's now say if T V sub L is not contained, that doesn't really look like what I wanted, but that's, so let me, didn't do much better, but that's supposed to not be in the span of the first L basis vectors. That's not B. And that's supposed to be true for each L. And that would be not B. If that's the case, then the span of V1, V2, V sub L cannot or can't be invariant because now we're picking a T, or I'm sorry, we're picking a vector in that group, V1 through V sub L, operating on it with T and showing that it's not in that group. Well, that's just the opposite of what we need for something to be invariant. So this can't be an invariant subspace of T. So then this span of V1 through V sub L can't be invariant because T acting on a vector in that span produces a vector that's not in that span. So we've just shown that if T V sub L is not in the span of V sub 1 through V sub L, then that implies that that set of vectors V1 through V sub L is not invariant, and that's not C. So we've gone from not B, we've shown that not B implies not C, which is the contrapositive argument for showing C implies B. So now we've gone in that direction. We've shown that C implies B by the contrapositive. We only have one thing left, and that is for B to imply C. And this one is, I hope, somewhat clean. If we have B, meaning T V sub 1 is in the span of V1, T V sub 2 is in the span of V1, V2, then C is true by the definition of what it means to be an invariant subspace, meaning TV1 is contained in the span of V1. That's the first statement in statement B. TV sub 2 is the span of V1, V2, etc. We now have TV sub L being in the span of V1, V sub L. Which means that V1, V2, V sub L is T invariant. These first statements, TV1 is span of V1, TV2 span of V1, V2, TV sub L span of V1 through V sub L, that's statement B. Well, just by looking at that, you can see that whatever you pick for L, TV sub L is invariant to the span of that set of vectors. And that's what statement C says. That V1, the span of V1 through V sub L is T invariant. So we've now shown and we're done with proposition whatever it was. There's too many tails ago, wasn't it? 512. Questions on proposition 512. And you can start looking at that in terms of that concrete example we started with that upper triangular matrix. And you can start to see that indeed these statements are equivalent in terms of a particular concrete example. Let's look at some other statements in Chapter 5. We may not be able to get through all of them, but let's examine some of those, and I think I may leave it up to you to work through some of the others. I gave you our goals in the beginning. Now you maybe have an idea of what I want you to start seeing relative to Chapter 5. Yes? So now the question was, if we were working through the proof, have we convinced beyond a shadow of a doubt that A implies C? Based on what we did, I claim we have. What did we do? We first showed that A was equivalent to B. So now we know A and B are equivalent. Then I said, oh, let's move on. Let's show B and C are equivalent. Okay, we bought that. Well, is A equivalent to C? Well, yes, if you believe that A implies B, which it does if they're equivalent, well, we just showed that B implies C. So if you want to see that A is equivalent to C, then just follow that argument that A implies B implies C, and just kind of erase B, and you now know that A implies C. And you can kind of play that in reverse. B was equivalent to C, and we showed that B was equivalent to A. So now we can start with C, go to B. Oh, once we have B, we can go to A. So we've indirectly shown that A and C are equivalent. Does that make sense? So no, I'm not going to show you that A is equivalent to C. We really don't need to. And besides, you're already asleep, right? So I've already read you a long chapter of the book, put you to sleep. Now I can leave and go to bed, right? Bedtime stories. But these are good bedtime stories. Chapter 5 is nice stuff. Eigenvalues and Eigenvectors. That's how Google has survived. It's the $25 billion eigenvector problem. And I need to post that so you can read it. Okay? What does it mean to be an eigenvector when you're Google? Well, it's this page rank. It essentially is how important are these pages in the entire web. And you can sort of show that as an eigenvalue, eigenvector problem. If you would have thought of that before, then maybe you would be in the shoes of the Google. So eigenvalues and eigenvectors can be quite important. Okay? All right. So now let's look at some statements. About upper triangular matrices. Again, I might abbreviate those as UT matrices. And we've already gone around enough with the proofs for today, right? So we'll spare you that and let you read that portion of the material in the book. Let's just talk about some of these ideas. First is Theorem 513. Suppose we are given E, which is a complex vector space. That's just a place that we get to play. But now what we want to do is introduce a linear operator on that space. Let's call it T. This now allows us to map vectors to vectors in that same complex vector space V. If we have complex vector space and a linear map T, then there is a basis of that vector space V where the matrix representation of that linear operator T is actually upper triangular. Now, even though the example that I presented at the beginning of class was dealing with real numbers, we're not guaranteed of this being true if we're on a real vector space. So this being a complex vector space is key. This is not necessarily true for real vector spaces. And now if we wanted to think about this in terms of given a complex vector space and a linear map, we know if it's an operator, which is that T is an element of L of V, then it's square. So we're mapping from the same space back to itself. We can now find a basis where we could just do an upper triangular representation. And that gives us a way of sort of simplifying our ideas or concepts. Let's now think about that structurally. An upper triangular matrix, if I just get crude and say the matrix representation, I'll just call T for now. It's a linear operator T also. But now if it's upper triangular, I have a hard zero below the diagonal. And then I have possibly non-zero elements on the diagonal, but up above it's something. It could be zeros, it could be numbers or elements of our field. If you look at the very first column, the fact that the first column has only one non-zero element, that means that the first vector of our set of basis vectors is actually an eigenvector of t and has an eigenvalue equal to lambda sub 1. And that was what we had actually in our example before. There's now an eigenvalue-eigenvector relationship. But we've also shown that when we have real vector spaces, sometimes we don't even have eigenvalues, do we? Remember a rotation in the xy plane? That doesn't end up producing an eigenvalue in the real numbers. So if t has no eigenvalues, which is possible for the reals, then it must follow that t has no upper triangular form. And we could generalize that. We could say, well, maybe it has upper block triangular form. We're not going to go there. Right now, we're just going to say upper triangular, so we have our entries on the diagonal. And that's what we're playing with. When we have complex vector spaces, this is nice. It plays nice with what we have. Let's look at another proposition. Proposition 16 in chapter 5. Suppose we are starting with a linear operator t, and that matrix representation of that linear operator has an upper triangular representation, which we're guaranteed if V is a complex vector space. So if T is a linear operator and has upper triangular representation, matrix representation, then T, this matrix representation, I should say, then the matrix representation is invertible if and only if all the diagonal entries of that upper triangular matrix are non-zero. Meaning if we have an upper triangular matrix, we can immediately inspect the diagonal entries. If any of those are a hard zero, we can't invert that linear map, can we? If it's not invertible, what do we know? It's non-injective. So it has a non-trivial null space. It's not surjective. We can't get to the entire space of our codomain. But if we want to know if a map is invertible, if somebody can show us that that matrix representation of that linear map in an upper triangular form, if they give that to us, we just inspect the diagonal entries. If they're all non-zero, yes, it has an inverse. That map is invertible. Another important result, like I said, now that we have proven that one, now we're just going to sort of state some results. So Prop 516 leads to one of the key results of Chapter 5. And that's Proposition 518. Again, suppose that we are given a linear map on this finite dimensional complex vector space V. I guess I don't need to make it a complex vector space as long as it satisfies these conditions. So given a linear map T on V, which has an upper triangular representation using some set of basis vectors on some basis, the eigenvalues of T are the diagonal entries of that upper triangular matrix. I'm not sure that this is much of a proof, but let's just sort of think about what we're talking about here. Suppose we now take this set of basis vectors, V1 up to V sub n, that's our basis that gives us this upper triangular matrix T. Using the notation of the book, that says that this matrix representation of T with respect to this set of basis vectors is now this upper triangular matrix. Now, what if we take and find a lambda in our field of numbers? And suppose now we look at the matrix representation of T minus lambda I in this same set of basis vectors. And we did this with our example, didn't we, to begin the class? What do we know happens with the eigenvalue eigenvector problem when we do this kind of a representation? If we call that eigensolutions, then we need to find vectors that are in the null space of this matrix if we get a good lambda, if we find the right lambda. So remember, the eigensolutions are associated with the null space of t minus lambda I. And that actually means we want t minus lambda I to have a non-trivial null space, which means we want it to not be injective. Otherwise, we would have a trivial null space, wouldn't we? So now what we want to do is remember that result. Was it Theorem 321? For some reason that rings a bell as far as this equivalence of invertible, subjective, or surjective, and injective. If we remember, when we're dealing with operators, injective if and only if surjective if and only if invertible. So being non-injective means that it's not invertible. So this is equivalent to saying that we want t minus lambda I to be non-invertible. And our most recent result or proposition talked about invertibility, didn't it? Our previous result shows that for an upper triangular matrix, to be invertible, or for the invertibility of an upper triangular matrix, then we need non-zero elements on the diagonal. Which then means if we choose these lambdas to be these entries on the diagonal, lambda 1 through lambda sub n, those are our eigenvalues that make that operator t minus lambda I non-invertible. And so those are our eigenvalues. So thus, lambda equal to lambda 1 through lambda sub n are the values that make t minus lambda sub I non-invertible, and hence are the eigenvalues of our operator T. Have a few more book chapters. I think we're all ready to keep going, right? To finish up chapter 5. But chapter 5 then starts talking about diagonal matrices. That's what? A specialization of upper triangular. You can have a diagonal matrix if you have distinct eigenvectors, which really is going to come, or linearly independent eigenvectors that form a basis, and those come from distinct eigenvalues. And we know a little bit about distinct eigenvalues and the numbers of those. So if we have enough of those, enough meaning equal to the dimension of our vector space, then we can diagonalize this matrix representation. That's true for generic complex vector spaces. That's not true for real vector spaces. In real vector spaces, we may only have second order or two-dimensional invariant subspaces. We may not have eigenvalues. That's what I want you to kind of finish up reading with chapter 5, and we'll get into a more specific vector space, meaning an inner product space, chapter 6, the next time we meet. That's the plan. See you then.